look at another problem here. Okay. Okay, so now this is another problem, and this is for a small sample. So we know right away this is a small sample size only 25, and we know in this case we're dealing with the t-test for sure, as we may often be anyway. Okay, so this is a two-sided test. First thing I'm going to do, let's see what are the number of fouls going regular different, number of fouls. Now same problem, except this time my sample size is 25. Okay, I'm going to change this number here. I'm going to change it to 35.95 just to make it more interesting. Okay, so in this sample of 25 games, this is the average that we got. Okay, so now I'm going to calculate my 95% confidence interval. How do I calculate my 95% confidence interval? First, I got to calculate my standard error. My standard error is going to be 5.8 divided by the square root of the sample size. Sample size was 25, so it's divided by 5. So my standard error is 1.14, right? That looks right. Everybody happy with that? So now what is my confidence interval? 1.16? Oh yeah, you're right. Yeah. That's 3 over there, 1.16. So what is my confidence interval now? My confidence interval is 35.95, right? Plus or minus. Okay, now what am I going to use for my t-score? Where do I get my critical t-score for this? Go to my t-table. Okay, what do I need? What t-table do I need to be 95% certain that I capture the real population mean? Okay, that's my z-table. Where'd my t-table go? Where is it? Okay, let's see. 95% would be this column right here, right? 24 degrees of freedom. So our number would be 2.064. So I would have to use 2.064 times 1.16. Okay, let's calculate that. I got my calculator out. Clear, clear. So I'm gonna first calculate 2.064 times 1.16 is equal to that. I'm going to put that into memory. First clear memory and put it into memory. I'm going to clear that out of the way, and I'm going to put 35.95 minus 2.35. It's going to be 33. Whoops. Hate when that happens. 33.
Deep breath. Brushing.
Clear. Let's see. Let me see. Was it 35.95? No, it was 30. I changed that number, didn't I? Yeah, 35.95. Can I still get it in there? 35.95 minus equals 33.555. 33.55, actually 6 if I round it off. Okay, and I can round it off because I'm at my end of my calculation here. Okay, comma, and at the high end, it's going to be, I'm going to clear that, 35.95 plus 38.344. Okay, so now let's compare that to what it is during the regular season. And during the regular season, it was 40.1. So 40.1, the regular season average, is outside of my confidence interval for the tournament, right? So I can say that those two means are different with 95% confidence, 5% chance of being wrong. If I want to do this as a again as a hypothesis test, we already outlined. I think we already outlined our hypothesis before. The mean during the tournament is not equal to the mean during the playoffs, or is equal or is not equal to it. Okay, this is two-sided tests, right? I calculate my t-score. My t-score is going to be equal to, it's going to be equal to x bar, which is 35.95 minus 41 divided by my standard error, which came out to be 1.16. Okay, it's going to be equal to let's see, 41 to be 5.05? Oh, 40.1. 40.1. Okay, not so simple now. Okay, use my calculator so I don't have to strain my brain too much. 35.95, 35.95 minus 40.1, 40.1 equals minus 4.15 divided by 1.16. Okay, and that comes out to be a t-score of negative 3.6. T-score of negative 3.6. What did my t-score have to be before to reject the null hypothesis? It was roughly for a sample size of 25 and 5% chance of being wrong for an alpha of 5%. What did we say that it was? Let's see if I can't get this to show me all of these things here. No. I don't know why it doesn't do that anymore. It's here somewhere. Here's a t table. Okay. Oh, that's my z table. Oh, here it is, all the way down here. That's why I didn't see it. Okay, for a sample size of 25, 24 degrees of freedom, I needed it to be bigger than my t critical was 2.06. Is it bigger? So it was 3 point something, right? So it is bigger, right?
But it's negative.
Doesn't matter, right? Because remember, I said it's either direction. It could be much smaller or much bigger. What we just showed was that the mean for the regular season and the mean for the playoffs were more than 3 standard deviations apart. Do we care whether the differences were which one was smaller or bigger than the other? We know that they're so far apart in terms of standard deviations that there's less than 5% chance that the means for the real populations are the same. Okay, so that's what this is really all about, to show that when you're roughly 2 standard deviations. That we introduced, when we started this, we talked about the number 2 being the number of standard deviation apart that you have to be 95% certain things are different. Remember, we talked about the empirical formula. Then we refine that for when we know the population standard deviation, not really 2, it's 1.96. Well, now, when we introduce the idea of the t-score has to make up for the fact that we really don't know the population standard deviation. We're kind of guessing at it. And the smaller sample size is, the worse that guess is. So the further apart we need these things to be to say that they're different. So as the sample size gets smaller, that t-value, the number of standard errors apart they have to be, gets bigger. That's why as the sample, if you go up in the chart, the sample size gets smaller, and the t-score that you need to exceed gets bigger and bigger. So in our case now, for a sample size of 25 or 24 degrees of freedom, we were at something like, what was it, what did we just calculate that to be? 3.57. 3.57, so at 24, 3.57 is bigger than the 2.06 that I need. It's even bigger than the 2.49 and the 2.7, but not as, it's even bigger than that one, isn't it? Yeah, so it's pretty far apart. There's less than 1% chance that we'd be wrong if we say that they're different, right? So that's kind of where you can bracket it with the t-table. But really, as far as the problem is concerned, all you needed to do is demonstrate that the t-scores, the difference in the number of standard errors apart that these two values are, is greater than 2.06, your critical value for the number of standard errors apart. Another word for that is number of your t-score. Okay, so I got some other examples here. Okay, I'm going to close this. Now, you can also do this for proportions, right? Except for proportions. Do I have one here? I don't have. Next one. There we go. You can also do the same thing for proportions. But for proportions, there's a special trick here. And that trick is that with proportions, we don't really, it's going to be very difficult for us to deal with this idea of the t-score with proportions, right? It's, like what sample size should we, it's one sample, and, how do we deal with this? So basically with proportions, you never really use the t-score, you only use the z-score. And the reason why you justify that is part of the assumption when you work with proportions is that you're working with large samples over 30. But there's a special caveat here. Not only do they have to be over 30, but both groups, the yeses and the nos, both have to be greater than 15. So you can't have a situation where you have a sample size where you go out and sample 30 people and ask them, if they own a motorcycle, and 2 people say yes and the other 28 say right. You got a sample size of 30, but that other group is too small to be accurate, right? So you need both of them. You need a sample size. You could have 15 and 15. That'd be okay because it's 30 and both sides are 15. But you need both sides to be at least equal to 15, and that the total be over 30. Okay, so now in this case, we're only going to use the z-score. So in this case, a test hypothesis of baseball home team win more often than the playoffs during the regular season. Okay, during regular season, we actually got a sample during the regular season. Each team plays 162 games. There's how many teams are there now? 30, 32? There's, I think, 30, 32, right? Whatever. That shows you how old I'm getting. I don't remember how many teams there are now. So 32 times 162 games, enormous sample. We're going to call that, and 58% of the time the home team wins, right? So that's we're solid. We're sure that that's the mean for the regular season because we have every regular season game. Well, we're only going to sample some of the regular season, some of the playoff games, and we sampled 64 games, and we found that 65% of the time the home team wins. 65% of 64 is how much? 65%. 40. Oh, so say 41 games. How many games does that leave for the other team to win? 41 less 64 less 41 is 23 games, right? So both sides are greater than 23, greater than 15. So we can go ahead and do this. Okay, so now how do I calculate my confidence interval for this? Well, I can calculate my confidence interval by saying, well, it's equal to, remember, you do the confidence interval for your sample, right? So my sample, P cap, right? My sample P cap is equal to 0.65. Okay, it's very easy to get confused here and say to yourself, oh, I'm going to start with the sample mean, 0.58. You know what the proportion is for 0.58. You don't need a confidence interval because that's a population proportion. You know all of this regular season games already. So you don't look at that when you only look at your sample. So P cap is 0.65. So now I have to find my standard error. And how do I calculate my standard error for that sample? It's going to be equal to 0.65 times 0.35, right? P times 1 minus P, times, divided by, it's divided by the sample size, which is 64, and I'm taking the square root of that whole thing, right? Nothing new here, right? Okay, and that's P times 1 minus P over N. Square root of that whole thing is going to be my standard error. Okay, so let's see what that's equal to. I'm going to get my calculator out. Okay, and I'm going to say, let's see, 0.65. I'm going to clear everything, clear my memory. 0.65 times 0.35 divided by 64. And then I'm going to find the square root of that. Comes out to be 0.059. Don't do as I say, not as I do. I'm going to round that off because I want to work with this. 0.06 is what that looks like roughly. Okay, now there's a reason why I don't want you to round it off, but I'm going to do it to save time here. So that's equal to 0.06. Okay, actually 0.0596, whatever it turned out to be. Okay, so now I want to calculate my confidence interval. What is my confidence interval? My confidence interval is P cap, just as I did with the with my proportions, with my means, my numerical means, plus or minus my a number I have to multiply by now. Remember I said, oh, So we're going to work only with sample size greater than 30, so we're going to use the z-score. So what number is it for a 95% confidence interval? 1.96, right? It would be 2.58 for a 99% confidence interval times the standard error, which is 0.06. Okay, see now I'm going to multiply my error. When I multiply this times this, I'm multiplying my error. It's making my rounding error bigger. But I'm just gonna actually do it 2 times 0.16. So it's going to be my p cap, which is 0.65 minus 1.2, 0.12, okay, is equal to 0.53, right? And the upper range is going to be 0.65 plus 0.12 is equal to 0.77. Okay, so my range for my true population proportion for playoff games is 0.53 to 0.77. Is my 58%, is it inside of that confidence interval or outside of the confidence interval? It's inside the confidence. So can I say that these two are different? I can't say that they're different because I'm comparing my confidence interval to a number that's not outside the confidence interval, so I failed to reject my null hypothesis. Now we can go ahead and use a z-score or basically same as a t-test, except for when we do a proportion, it's going to be 0.65. I'm just going to use a bigger number first. It doesn't really matter because remember we just demonstrated that it doesn't matter if you go negative or positive, right? So it really doesn't matter if you put p0 minus p cap or p cap minus p0. It's going to work out. The sign's going to change, but it's going to work out the same anyway. So 0.65 minus, what did I say it was? 0.58? 0.58 divided by my standard error, which turned out to be 0.06. Okay, so that's going to be equal to 0.07 divided by 0.06. Okay, and that's going to be equal to we'll say 1.2. Okay, a z-score of 1.2, is that enough for you to reject the null hypothesis? Right, z-score. What z-score do we need to reject the null hypothesis? We have to be 1.96. We need them to be 2 standard errors apart, right? So 1.2 is going to be too small to reject the null hypothesis. So just as we did with our confidence interval, we failed to prove that they're different. So we failed to reject the null hypothesis that the proportions are the same, and and so that's it. We're done, right? So proportions, whether it's proportions or numbers, you do the same thing. You calculate calculate either a confidence interval or you do a hypothesis test and calculate the z or t score, and you compare that to the critical value you need to exceed to say that they're 2 standard errors apart, at least for a 95% confidence interval. Or if not 2, then what little bit more than 2 you need for a t-score because it's a small sample. So now I got a bunch of examples for you guys to work on. The t-score, no. The 2 times only comes when you go to the chart and you look up the probability. Like in other words, remember with proportions, we're only interested in the disease table, right? Because we're working with big sample size. We don't use this t-table. Okay, so that 1.2 we just calculated, well, we're going to look that up right now. The p-value, remember that what was our z-score? It was 1.2. Okay, and why can't I find it? Where did it go? Let's try this again. Double click. Okay, bring it up front. T-table. There it is. Okay, I must have minimized it. No, that's the one I want, the z-table. Okay, window. Z-table. There it is. Okay, so our score came out to be 1.2. 1.20 represents an area to the left of 86.43. I'm going to call it 87, right? 0.87. Okay, so that means that 87% of this distribution is to the left of that. That means that this tail, the probability of my being wrong is always in the tails. This tail is 13%. That'd be okay if it was a one-tailed test. Since this area that I got from the z-table for 1.2 is only 13%, but it's a two-tailed test, I got to account for the other part at the lower end. So it's 13% and 13%. So my chances of being wrong, if I reject the null hypothesis, would have a z-score of 1.2 is 26%. Okay, that's why I double it, because I got to account for both tails. Okay. Again, I can see, yeah, it's a little bit confusing. I have to admit it. Okay, let's take a look at these exercises. The mean SAT score for a population of first-year students at Hunter's is 620. The standard deviations of scores in this population is 95. Am I talking about a sample of population? I use the term population twice there. It's population. Everybody at Hunter takes the SATs, so we know the true average and we know the true standard deviation. An investigator believes that the SAT of first-year psychology majors is significantly different than the mean score of the population. The mean of a sample of 36 randomly selected psychology majors is 658. Okay, you guys work on finding the confidence interval for the mean SAT score for psychology majors and tell me if you can tell me if those two means are different. Okay, I'm going to give you a couple of minutes to get ahead of me. How are you guys doing online? Okay, good. Can you use either method? In a single sample test, there's almost perfect agreement between the 95% confidence interval and the t-test. Okay? When we get into other kinds of samples, like paired samples well, maybe not paired samples, but independent samples with equal variances and different variances, when we move on to other things, we're really when we want to compare means, we're going to be using the t-test. We're not going to be using the confidence interval. Okay, so for this kind of situation where it's a single sample t-test, I can't easily imagine a situation where you would get a disagreement between the confidence interval and the t-test because you're really using the same table, the t-table, to do both calculations. However, there are more complicated calculations we're going to wind up doing later on where we just do the t-test to compare means. In other words, our fallback way to compare means in the future is going to be the t-test. Okay, when we're comparing two means. Okay, when we're comparing more than two means to each other, things get a little bit more complicated. We'll work with something else. Now, let me go back on some of the questions. 2.58. Oh, okay. So yeah, 2.064 was the number of standard deviations apart. Okay, and that represents your certainty, the likelihood of getting values that far apart. So for 2.064, that we had 5% chance if it was two-tailed test, 2.5% chance of getting a higher value, 2.5% chance of getting a lower value. So if you have a t-score that exceeds that, you have a less than a 2.5% chance on either end, or a total of 5% chance of being wrong if you say they're different, because that's how unlikely it is to get that extreme a difference in the two values. Okay, so you guys get a chance to work on this a little bit, and I'm going to pick it up in a second here. So I'm just going to write in here. I'm just going to transfer this information while I'm waiting for you guys over to my graph paper so I can write on it. Okay, let me see. Okay, Okay, the mean for 100 students is equal to 620. Standard deviation for the population is 95. Sigma equals 95. Okay, and mean of 36, sample size is 36. And X bar for that sample is 648. Okay. Good. Okay. Okay. So I'm going to start with the confidence interval. So you guys, see if you guys did the same thing that I did. Okay. First of all, I know that the mean for all Hunter students is 620. So I don't need to do anything with that. I know that mean. That's all students at Hunter. That's the entire population. Now, this is my sample of psychology majors. Was it psychology majors? First year psychology majors. They had an average of, they have an average SAT score, verbal. I'm going to guess it's the verbal score, not the math score, based on what I know from your psychology majors. Okay, so 648. So now I'm going to go over here, a little dig at the psych majors. I'm going to go over here and I'm going to take a look at what I need to, what does that tell me about the mean for all psychology majors? I don't know the mean. I don't know the mean for all psychology majors, right? I don't know that mean. All I know is what this sample mean is. Okay, so my sample mean is 648. So now I need to find a confidence interval for my psychology majors mean. Okay, so my confidence interval is going to be equal to X bar plus or minus. Okay, now I gotta figure a value for here. Anybody propose? Is this going to be a T score or a Z score? It's a little tricky here, right? Right. It's going to be what? It's going to be a T score.
No.
It's going to be it's going to be, where, do you know what the sample standard deviation is? Did I tell you the sample standard deviation? The only standard deviation you know is the population standard deviation. You know sigma in this case, right? I gave you sigma. So we're going to use the Z score. Okay, everybody okay with that? A little bit of a twist there, right? So it's going to be 1.96. Had I told you that 95 was the standard deviation for my sample, you would have figured, oh, I got to figure standard error is going to be, then you would have figured you were going to use a T-score for 35 degrees of freedom. Okay, and we would have gone to the table, looked that up. It probably would have been something like 2.03 or something like that, right? And that's what we would have used instead of 1.96. Okay, but in this case, I gave you the population standard deviation, and I didn't even bother to give you the sample standard deviation. I assumed that it was going to be roughly the same as the population standard deviation. Okay, times my standard error. I still got to calculate my standard error because we're dealing with the sample means, right? So my standard error, if I was looking for information about the population, what percentage of people are above this score, what percentage of people are below that score, I would just use the standard deviation or sigma. But when I'm dealing with what's the distribution of sample means, I need the standard error. So we want to know how spread out would be, how would I expect samples of size 36, samples, the averages for samples of size 36, how spread out would I expect them to be? And that's going to be equal to sigma over the square root of n. And n, square root of n is 30, and that's 36, it's over 6. That's equal to, let's see, 95 over 6. And that's equal to 1 and 35 is 5 and 5, 6. What's 5, 6? What's that? 866 or something like that? 83? Okay, I'm going to leave it at 83. Okay, so my standard error is 15.83. So let's calculate this. 648, remember it's X bar, not the population. Right? I find confidence intervals for my sample mean, not my population mean, because I already know what my population mean is. I don't need a confidence interval. Plus or minus 1.96 times 15.83. Okay, get my calculator out. Okay, 1.96 times 15.83 equals 31 point, whatever. I'm going to put that into memory. And I'm going to clear it. Let's see, 648 minus that value is 617. I'm going to round it to 617. And the upper limit is going to be, for our 95% confidence interval, is going to be 648 plus 1.96 times our standard error is equal to 679. Okay, so that's the range within a 95% certain that my true mean for my psych majors is going to be. Can I say with 95% certainty that it's different than 620, which is the whole population? You know, I thought I was so careful to make sure that this one, we actually got a difference. I'm going to change the mean this is 610 now.
You do it.
Can I say that they're different now?
Yeah.
Yes, I can. Right, finally. Okay, good. The other way I can do this is hypothesis testing. What do I do with hypothesis testing? H null and H alternative. Now, I'm not going to worry about, we might have said something about he thought they were higher and stuff like that. I'm just going to say different. So for our purposes, I'm going to make this a two-tailed test. A lot of times, when you really suspect that something is higher than the other, you may do a two-tailed test anyway because it's a more rigorous test. Okay, so a lot of times you'll ignore the fact that your real suspicion is that they're higher. You don't have any real evidence of that, though. I don't know. I just had a suspicion. I don't have any real evidence. The only time really that you're justified in doing a one-tailed test is when you know that there's something that constrains this outcome from not going the other way. An example might be doing a test of a drug, and you want to know whether it lowers blood pressure, and you happen to know that this drug is a vasodilator. Well, if it's a vasodilator, it doesn't seem very likely it's going to increase your blood pressure, right? Right. So you might argue that this drug can only lower blood pressure, and you want to prove that it lowers it there's a significant difference. Maybe you could do that. Drug companies are notorious for liking single-sided tests because they're easier to prove. You don't need as big a sample size for a single, right? I mean, that's in their interest. Okay, so my null hypothesis is going to be the mean of all the Hunter students is equal to the mean of the psych majors, right? Okay, so now my alternative hypothesis, mean of Hunter students, does not equal the mean of psych majors. Okay, so how am I going to prove that? Well, since I know the standard deviation, I'm going to use z-score here. And z is equal to x bar, right, which is x bar minus mu over the standard error is equal to, in our case, 648 minus 610 over the standard error, which is 15.83. So that's equal to 38 over 15.83. And that's equal to a z-score of, or in other words, how many standard deviations apart, standard errors are these apart? 38 divided by 15.83. Okay, 2.40 equal to 2.40. I'm already the fact I'm above 1.96 or above 2 makes me feel real good about this, right? So now the z-score is 2.40. What p-value does that represent? How do I determine that? I go to the z-table, 2.40, right? I'm interested in the areas at the end in the tails. Two-sided test, I'm going to look at both tails. So 2.40. 2.40 is 99.2%. So that means the only thing left in that tail is 0.8% at the high end. I double that because I also have the low end, so it's 1.6%. So my p-value for the two-sided test is 1.6%. So I have a 1.6% chance of being wrong. So do I reject my null hypothesis? 0.16, what? Do I reject my null hypothesis? My p-value is 0.016. I reject if p is less than my acceptable level of error, right? Which is alpha, which is 0.05. So I got 1%, 0.6% chance of being wrong. I'm willing to accept up to a 5% chance of being wrong. So I reject my null hypothesis and I accept my alternative hypothesis that the means for Hunter students in general is different than the means for psych students. Okay? Yeah, you could. That would be a t-test. That would, in a t-test, you would say that 2.4 is greater than your critical value for z or t, which is 1.96. And the only thing that this last step with the p-value does is it tells you how much lower than 5% your chances of being wrong are. Right? That's what the p-value is. In other words, here, let me just show you this one more time. This chart. Okay. What this chart is, this entire chart represents all the possible outcomes for this population. In other words, you could get there is a chance that you could get a mean which is over here. You could get a mean. It's more likely you'll get a mean over here, but there's a chance you could get a mean over here. There's a chance you could get a mean over here. At some point, you can say to yourself, well, what are the odds of Mike from this population getting a mean that's smaller than this number here, which is a z-score of 1.96? Well, it's only 2.5%, right? Well, what about a z-score of 2.58, negative 2.58? Well, that's over here. The chances of getting something that's further away from the population mean than than a z-score of 2.58, the chances of that occurring are only 0.5%, 1% if you look at both ends, right? 99% confidence, right? So the idea here is you want to be so far away from the mean that the chances you would get that outcome from this population is very, very tiny. And because we have limited resources, we usually accept a chance of 5% error. In other words, we allow the difference in the mean for the population we're looking at, the sample we're taking, compared to the other population, we allow for it to be as close as 2 standard deviations or 1.9 standard deviations, and still reject the mean, still reject the null hypothesis. You guys pretty comfortable with this a little bit? Are you kind of getting there, kind of getting the feel for this? Okay, you want to try one more? Oh, it's kind of late, huh? No. Once you reject the null hypothesis, you've proved the alternative. When I say proved, you've proved it with that level of certainty. Okay, and remember, you could easily say your alpha error is 0.01, right? 1% chance of being wrong, which would be the same as a 99% confidence interval, right? Most studies, we're happy with 95%. I don't know about you guys at home, but they're giving up here. I couldn't get them to stay for another example. You guys still there? Did you fall asleep? Okay, they're still there. Wusses. They're calling you wusses. That's what's happening online. Okay, guys. Who's lazy now? Yeah, they're saying who's lazy now? I'm sorry. They're on there. If you look under the section, the lab section 003 and 004, they're in there. You can download them and stuff like that. And I will put up answers to the ones we didn't do. Okay.
No.
Okay. And the other thing I'm going to do is the homework grades were pretty good. The homework grades were pretty high. I would say at least half the class got either in the quarter, like probably about a third of the class got between 95 and 100. More than third of class, maybe half the class. If you're above 90, you're in good shape. I graded it from 60 to 100, basically 5 points per problem, right? So if you got 95 and above, you seem to get the idea pretty well of the material we covered in assignment 3. If you got between 90 and 95, you made some sort of mistake in there somewhere that you lost track of maybe one problem that you had a glitch on, 1 or 2 problems you had a glitch on or something like that. Still in pretty good shape. If you're in the 80s, you really need to go back there and look at those things more carefully and do the homework. If you got under 80, if you got under 85, you should really seriously go back and like maybe look at the lab session from last week or something like that and really kind of review it a little bit, right? So that's kind of like when you look at the grades, kind of judge it that way. That you want to be in the 90s, and yeah, if you're in the 90s, you're in pretty good shape.
And are they
Yeah, all the grades are posted. Also, the answers to the assignment 3. Assignment 4 is in progress. I don't know, they put it on Blackboard. Hey, good night, guys.
Give me a